Okay, let's get started. So welcome everyone to another lecture in our ID 5130 Parallel Scientific Computing course. Okay, so in the last lecture we looked at essentially some semantics, right, or details of MPI send and receive, right? So we saw essentially exactly what happens when we use a send and a receive command on different processes. How does the buffering and blocking happens and all sorts of things. Okay, so so that is nice and good, but we should also kind of learn a little bit about the numerical methods and applications. So as a result, let us look at the first example that we started off in the OpenMP as well, the trapezoidal rule, calculation of integration of a function on given set of limits using a numerical method, right? So essentially, let's look at the trapezoidal method or the trapezoidal rule using MPI parallelization. Okay, so before we apply MPI parallelization, let us kind of quickly recall what does the trapezoidal rule do. It basically, if you have to evaluate integration of a function over a limits a to b, then numerically, if you can split this function into regular intervals that are basically dictated by the length of the integration h, right? If you can split this into n intervals, then this value of integration is numerically approximated to be equal to h times f of x0 by 2 plus f of xn by 2, right, plus you have f of x1, f of x2, all the way to f of xn minus 1, right? So wherein we say that if you can represent a as x0 and b as your xn, then x0 and xn are the endpoint values, and these are all the other values that are kind of there in between, right? So basically, if you have a function, this is x and this is f of x, and then if you have, let's say, a function representation, and if you were to calculate numerically the area under this curve, so that's basically would be given by several intervals, as we have seen before, right? And we are also assuming that all these intervals are of uniform width, so the width of each of these is basically your h, that is equal to b minus a, that is the this value minus this value divided by the number of intervals. And then, of course, because you're using a numerical integration, you're going to basically approximate these as trapezoids instead of this function, right? So this is the continuous function f of x, whereas the area would be only the area under these curves, right? I think that you all understand. Now, how do you go about calculating this integration? Let us say if your n, the number of trapezoids, is large, then how will you calculate it using MPI, right? If you want to use distributed memory programming, how will you go about it? That means, let us say if you have the number of processors you have in MPI that you want to run with is, let's call it as n procs, or this is basically your communicator size, right? So if you have a communicator size of certain values, so or n processors, then we assume that the number of trapezoids you have is kind of evenly divisible by n procs. Okay, so basically you would like to assign n by n procs number of trapezoids to each of the processor, right? Each of the process. That means we would like each process to calculate a certain number of area under a certain number of trapezoids, and then essentially we would like, this, let's say we assign first 2 to one process, and then the next 2 to another process, and so on, and then eventually we would like to calculate by calculating the areas, okay, of all these things by summing them up, right? So essentially we would like to calculate integration over these by assigning to different processes, right? So this is, let's say, P0, P1, P2, and P3, right? If you have four n procs. All right, so I mean, essentially this is n procs minus 1. It will kind of go to n procs minus 1, or you know, n procs would be the total number of process. Okay, so that is the idea. Essentially, you would kind of distribute the work to each and every process, and then they calculate the area under the trapezoid, you know, under the function that depending on the limits, and then once they calculate the areas or they calculate these values, each of them would kind of send it to a particular process, and then that process would add all the values and print the final sum of all these things, which is basically the integration. Okay, so let us kind of try to write a kind of an algorithm before we go to the code. So the first thing we should do is we should basically define or assign values for a, b, that is the limits of integration, and n, that is number of trapezoids, and then we would also have to define how many processors are the communicator size that we would like to work with, right? Okay, once you have that, then you would basically calculate what is h. H is the step size, that is your b minus a upon n. Okay, then now because each of the process would be kind of going to work with its own you know range here, so we need to kind of define a and b as being local to each and every process. For example, for process 0, local a, local b would be these. For process 1, local a, local b would be these, and so on, right? So for each of the processes. So that means I would define new variables, which I would like to call it as LA, would be local a, that would be equal to, or I would first define local n, that is basically number of trapezoids that belong to each process would be n upon n procs, right? Similarly, I would write LA would be equal to the local a, that is equal to a plus, if I denote the rank of each process by my ID, it would be my ID times ln times h, right? And then your local b would be your local a plus ln times h, right? That's what you'd have. And then once you have this, you can calculate your local sum, that is basically the evaluation of the integral, like essentially evaluation of this some of these functions for the trapezoids that belong to a particular process by calling the trapezoidal rule function, and this would be basically you would pass local a, local b, and then local n and the step size, and then it would calculate the local sum. Then once you have the sum calculated by every process, remember that this will be executed by every process, then we should kind of somehow send these local sums and calculate the global sum. That would be our total integration. So for that we can use a very simple formula, very simple rule, that is basically if my ID is let's say is not equal to 0, that means you are not the 0th process, then what you need to do is you basically send your local sum to process 0, right? And if you are the process 0, right, that means if you are the process 0, what you need to do is you basically calculate your let's say total sum equals, assign to your local sum, and then you would receive from every process. So let's say for processor equal to 1 to processor less than n procs, process plus plus, so from each of the process you would receive, so basically what is this? This is receive. Okay, receive local sum from process, right? And then once you receive it, you add it to your t sum. So t sum would be equal to the local sum that is basically received, right? So whatever you received, you would use it here, right? Once you do that, and then if you happen to be process 0, you would basically, if my ID equals 0, then you basically print your total sum, right? So that is going to print your total value of the integration. So that is kind of a very distributed memory programming based trapezoidal rule. It basically involves sending and receive, which were not there, if you recall, in the OpenMP kind of calculation, right? So in OpenMP we were more worried about data that is being local and global, or trying to do the reduction operator and things like that. Here our focus is more on distributing the work and then collecting the work and then calculating the final sum. Okay, so that is kind of the contrast. So let us take a look at the code. So to do this, to essentially write an MPI version of trapezoidal rule, I have started off with the, you remember the OpenMP code that we have written. I started off with the OpenMP code and kind of made changes in that. And so I'm going to kind of show you the final code instead of showing you all the edits, because I don't think that is required at the moment. Okay, so what I did was basically you have this. Let's look at this. So basically the code is similar to the pseudocode we have written. So you have int main, it takes in command line arguments if they are provided. Then you have the definition of the variables here. Declaration a, b would be the limits. Final result is where we would calculate our integration. LA, LB, LSum, H. So LA would be the local A, LB would be the local B, LSum would be the local sum, and H is the step size. And then I also define my ID. This is basically the rank of the process, and prox to be the size of the communicator, number of processes involved in the current this thing, and then process is basically just a loop variable. Okay, and then I have int n that defines the number of points or number of trapezoids that we would like to work with, and then ln denotes the local number of trapezoids assigned to each process. Okay, then as you recall, the first three commands in the first command is basically MPI initialize, and we don't intend to pass any of these command line arguments, that is argc, argv. So as a result, we just put in null comma null here, and then the next two arguments are related to the MPI com rank and com size, which will fill essentially it will fill what is the my ID depending on the ID of the process that it is executing, and then the number of process. This is the size of the communicator, right? So basically this is the size of the communicator, and then this is the my rank of the process, or rank of my process. Okay, then what I have done is here is I have kind of hard coded to be the number of trapezoids here, right? Oops, or rank of the process. Then we have the number of trapezoids. Okay, and then we have I'm integrating from 0 to pi, and then final result is basically initialized to 0. Then of course we calculate what is h. H is your b minus a upon n. Then assuming that the n prox evenly divides the number of trapezoids. So we just basically divide ln equals n by n prox, and then you set the limits. LA equals a plus my ID times ln times h, and then local b would be always local a plus number of local trapezoids times the h. Okay, then what we do is that LSum equals, we are calling, so basically this also will be called by every, all these things will be called by every process, right? So every process calls this function. Well, not only this function, all other lines as well will be called by every function. So every process calls this function. So every process will use its own local a, local b, local n, and the h, which is the global step size, and calculate the trapezoid rule, basically calculate the area under the curve that it belongs to, and then return that variable in value into LSum. Okay, that is the local sum. Now that is all it is. Okay, then let's go to look at trapezoidal rule. So this is returns a double value and takes in local a, local b, local n, and h. Okay, those are all being arguments here. Then we define some couple of variables here, x and total, and then integer I. So basically total would be equal to function local a plus local b by 2, and then for I equals 1 to local n minus 1, I plus plus. Okay, I would calculate this value, right? This is x equals LA plus I times h, and then calculate total equals total plus function h, and then multiply with h. Okay, so that's basically your formula, and then return the total. Okay, so that's what trapezoidal rule would do. And once you have the local sum calculated by each and every process, we would come down here, and then now we should kind of sum all these local values into a global value. For that, what we're doing is we're designating process 0 as the one that will receive all the local sums, and it will add it. So if my ID is not equal to 0, so as per the pseudocode we have written, if my ID is not equal to 0, that means other than all other zero process, they will kind of send. So you have MPI send, you send local sum. Local sum is a 1 value and it is of type MPI double, right? And then you are sending to 0, and then next 0 indicates the tag, and then the communicate world indicates the communicator. Okay, so that's what we have. So if I repeat again, this is the location of the address we are sending, that is ampersand L sum, and then 1 is you're sending one data, right? That is 1 value. Then you are sending variable of type MPI double. You are sending it to process 0, and the tag is 0, and then MPI communicate world is the communicator. If you are not the process, if you are the actually if you are process 0, then what you need to do is you need to first initialize your final result equal to L sum. That this L sum is calculated where it was calculated by 0 here, right? Oops. So this is process 0. Okay, so L sum is calculated here. So whatever is calculated here by this guy would be coming here. So once you initialize with that, initialize final result with that, then you receive for every process 1 equals process less than and process plus plus, you would receive L sum. Okay, it's already used up here, so we can use it here. So L sum is the value will be received into L sum. You are receiving 1 value of MPI double type, and then it will be received. So this is the source from where it should receive. It should receive from process, and the tag it should receive with be 0, and then MPI communicate world. Then you have either you can declare a status as MPI status, or you can even ignore if you do not want to examine this later on. So I just used MPI status ignore. This is the wildcard argument that we discussed yesterday. Okay, and then finally once you receive, you just basically add it to final result equal final result plus L sum. That will calculate the entire global sum. Okay, and then once you have the global sum calculated on process 0, so process 0, if it is ID equal to 0, it's going to print this value saying that the area under the curve 1 plus sin x, that's basically the function we are trying to integrate, between 0 to pi is equal to such and such. Okay, and then you basically print the final result. Okay, now you also recall that MPI finalize is the last function we should call, last MPI function we should call in any MPI program, and then basically return 0 would return it to the operating system. Okay, so that's what we have, and then this is the trapezoidal rule, and then this is the function definition. If you recall, we also earlier included openmp.h. Now I include #include mpi.h, and then math.h because I have used the sign function. Okay, so that's about the program in C. Of course, you can write a corresponding program in Fortran, starting with either the OpenMP version or the serial version, which I'm not going to show in the interest of time, but you can do it and then kind of run it similar to what we do here. Okay, so then let us see if we can compile this program. This is basically MPI program MPI trapezoidal v1.c. So I would use MPI cc. I could use -g, or I can even directly compile program MPI trapezoidal v1. I call it v1 version 1 because we can improve upon this version depending on a few things that we discuss later on in today's lecture. Okay, so I would do that, but I also need to link to the math library, so I would say -lm and then compile. Okay, it compiles without any errors. Then I would say MPI run -np number of processes for /a.out, and it just basically prints the value of pi to be 5 point, so area under this 1 plus sin x between 0 to pi is 5.14159. That seems to be correct. Let me do it with a few less processes, with 2, because I have anyway set the number of elements to 1024. It is fine to divide with 4 as well, or you can even do you can even do, let's say, maybe 8. Let me do maybe 8 divided. Okay, so I can do this, or maybe I can even go with I mean, that is fine. Okay, so we have this. Then okay, so it basically is running. Then okay, so that's about the code. But then there are a few things we need to pay attention to. One is the number of points, that is number of trapezoids, as well as the limits are now kind of hard coded, right? Okay, they are kind of hard coded. So if you were to avoid this, like in the case of open MP programmer. So if you want to kind of give how many A, B and N, then this kind of needs to be basically taken from the user. Okay, so and then also the final result is basically only printed by process 0 here, right? So basically the output is only printed by process 0. So in this context of taking in the values and the output, let us discuss the input and output handling in MPI. Okay, so basically dealing with input and output. Okay, so let us see output first and then we'll come to input. So when it comes to output, essentially MPI implementations will provide complete access to std out, that is the standard output, as well as standard error to all processes. That means all processes can print to standard output. Now of course you would realize that if all process trying to kind of trying to write to the same location as in standard output, then there can be a kind of a competition, right, between the processes, right, to write it to the standard output. So that some kind of a racing condition might come, but eventually they will write the output to standard output. Only thing is that this can be the order in which processes print to the screen is unpredictable, right? So that is basically non-deterministic. But if you do not really worry about the order in which it has to print, then you can let all process print something to the screen as well, okay, as well as to the error, to the standard error. Now in our particular case, of course, we didn't have to, or we could not do that because all processes kind of sent their values to process 0, right, and process 0 could only print it to the screen, right? Okay. All right, now if we talk about input, unlike output, MPI, most of the MPI implementations only allow the process 0 to kind of handle the input. This makes sense because if you are kind of keying in some values, then it is kind of ambiguous on basically how this input should be processed by each process, right? Because should process 0 read the first line, or second line should be read by process 1, or third line should be read by process 2 or something, or how should this be read is kind of causes an ambiguity. As a result, only process 0 is allowed to, in most MPI implementation, process 0 only allowed to kind of take in the input. That means what we need to do is, if we were to instead of hard coding the values of N, A and B, if you were to take in the input, then the scanf and printf statement should kind of happen later. So essentially should basically happen on process 0 only, and then process 0 should be sending this data, right, because this data is kind of the global data that is basically required by all processes. Okay, should be sending this to all processes after being read by process 0. So if you were to write some kind of a pseudo code for the input, essentially if my ID is equal to 0, then process 0 would basically read the values. So you basically printf enter values of A, B, N, okay, and then you would say scanf percentage whatever LD, or depending on the values, they'll read in the values, Then for process equal to 1 to process less than n procs, process plus plus, right? So for each of the process, you basically have to send it to send these values. So send ampersand a, okay, and then similarly write another send MPI send ampersand b. Okay, you have to put in the right data type here, and send ampersand n, send in the value of n, right? I'm kind of writing this code here. And then if you are not process 0, then you basically receive the values, right? So you would just receive MPI receive ampersand a 1, and then you would have another MPI receive ampersand b, you will have another receive MPI receive ampersand n, right? And then these values. Okay, so you would write a code like this, which will basically take care of the input that is being read from the user. Okay, basically to read the user input. Okay, so that is kind of about the input output handling. That means you can of course go back to this particular program that we have seen here and change this so it's such that you can add another function, or even here directly, wherein the input will be read by process 0 and it will be communicated to all other processes, and you can kind of modify that. Okay, so that can be done, and you can call that as version 2 or something like that. All right, so so far so good, but you can, and if you kind of recollect from our first few lectures in the course, we talked about in the context of parallelization. We said sometimes it is probably kind of step back and then look at the problem from a fresh perspective rather than trying to parallelize the existing serial code. And in that context, we said that calculating this global sum, right, or in our case the final result, you remember, could have happened instead of all process sending it to 0, could have happened using a binary tree like structure, right? Structured communication instead of this, right? Because if you look at it now, what's going on is let's say if you have, let's say, a number of threads is, or number of procs is 8 procs. If you have let's say 8 process, then what happens is that all the process from 1 to all the way to 7 would send their local sum to process 0, right? And process 0 would receive 7 values, and it has to add these 7 values to calculate your final result, or we call it as the total sum or whatever, or the global sum, right? Okay, so whatever you call it, essentially, so process 0 has to receive 7 values, 7 doubles, and then it has to add 7 doubles, while all other processes are basically idle, right? That means what the all other processes are doing is they are just instructing, okay, they are telling process 0, okay, here it is, take this value, and then they are instructing it that you just add this value to whatever you have, and then they are sitting idle, right? This is basically like, if you look at the TA's example, there is only one TA, essentially doing all the work, and all the TAs just instruct them, just grade all of these and then just sum the values. That is kind of wasting the resources, because all other processes are kind of sitting idle instead of participating and reducing the work. So this can be certainly is not a good way to calculate the global sum, right? Because there can be some kind of an optimized version of it, which according to what we discussed can happen, and we can certainly improve. There can be there is a scope for improvement in the program. In the calculation of the global sum part. Okay, that means if I kind of recall, if you recall, basically we have certain values 0, 1, 2, 3, 4, 5, 6, 7. Okay, so basically 0, 1, 2, 3, 4, 5, 6, 7, let's say we have nprox equals 8. Right now all of them are sending it to 0, and 0 is basically adding. That is basically 7 receives and 7 additions. Instead what we said was, of course, you know, I mean, there are some values here. Let's say you have 10, 20, 15, some values here. Okay, I'm not kind of writing these values. Okay, we have some values here. Now, so instead, essentially 1 can send this value to 0, and 0 can receive and add it, and similarly 3 can send it to 0, 2, and then 2 can add it, and similarly 5 can send it value to 4, and 4 adds these two values, and 7 sends it to 6, and 6 adds these two values and calculates another value. Let's say 30, I know something here, so maybe 10, 25, some values here, 56, 35, 56, something. Okay, then in a next step what can happen is that essentially 2 can now send it to 0, and 0 will receive and add it to a local value. Similarly 6 would send it to 4, and 4 would receive the value and add it and calculate the sum, and eventually in the final step basically 4 would send the value to 0, right, and 0 would add the value and calculates this is the total sum, right, or the final result. Okay, so that is the final result. Now what we said is that this is much more faster, because all the process, of course, I mean not all the processes are actually working, because here also half of the process, such as 1, you know, 1, 3, 5 and 7, what they're doing is basically they are instructing, instead of instructing 0, they are instructing somebody else. For example, 3 is instructing 2 to, okay, take this value and add it. After that they are sitting idle. So for them the work is not, hasn't improved much, whereas for 2 it's kind of doing little more work, because now 2 is receiving and adding, and it is sending to the next value, whereas 4 is doing a lot more work compared to what it was doing earlier. So but now assuming that all all the receives and additions take kind of roughly start at the same time, and then they almost take, let's say, about the same time, then what happens is that the calculations now can proceed in parallel, and as a result 0, instead of receiving 7 values earlier and adding them, now it has to only receive 1, 2, 3 values and add them. Okay, that means process 0 now has to receive only 3 values and make 3 adds. That's all, to calculate the values, right? So instead of the original version in which it has to receive 7 values and make 7 adds, so this is basically an improvement of more than 50%, right? So that kind of saves, that we have saved time by more than 50%. Now things get even better. Let's say if your nprox, instead of being 7, if it is, let's say, 1024, if you have 1024 processes, this is not uncommon in certain simulations in engineering applications. So if you have 1024 processes, then essentially process 0 in the original version has to receive 1023 values, needs to excuse me, needs to be received and added, whereas in the tree, in the binary tree structure like addition, right, process 0 only has to receive 10 values, right? 10 values needs to be received and added. So this is actually much faster, because it's kind of, instead of 1023 you have 10, so this is basically more than a factor of 100, right? Faster, right? So this is certainly much more quicker and beneficial to use such communication, rather than sending it like, rather than all processes sending it to 0 and then all other processes are sitting idle. Of course, now the thing is that this tree-like structure communication is not kind of unique, because you can say, well, why do we have to do it this way? I can come up with another way of doing this thing. So for example, you could say I have, let's say, 0, 1, 2, 3, 4, 5, 6, 7, right? Instead of the odd processes sending it to the even processes like what we have done here, what we can do is now we can kind of split into half, and 4 can send it to 0, and 5 can send it to 1, 6 can send it to 2, and then 7 can then send it to 4, right? For example, things may proceed like this, right? And then we have basically, so this could be the first step. After this, again 2 might send it to 0, and then 3 might send it to 1, okay, and then the sum could proceed like this, right? And eventually 1 might send it to 0, and then 0 would calculate the value. So there are certainly several ways of implementing kind of a this tree-like global sum, right? So as a result, there are several ways, and we would not know a priori which one would be better. For example, let's say a particular tree structure might be best, let's say, on a small number of procs. Okay, you might find that a different version might be best on large number of procs is there. Or even worse, what we can see is that a particular method of this global sum calculation might be best when you have, let's say, when you're working with a particular system A, and another version could be better on system B. So essentially we end up doing, essentially we kind of get dragged into this endless optimization choices, right, for our global sum example, right? Because we would not know what works best on a particular machine. So in order to kind of so does the user or supposed to implement each of these on a particular machine and then see whether it works fine or not? Well, no, that's not what we have to do. So rather, to kind of with the existence of this limitless possibilities of writing this kind of global sum, it's kind of very unreasonable to expect each user to the MPI programmer to kind of write an optimal global sum for his calculation. As a result, MPI takes the responsibility, and MPI provides a global sum, okay, that basically takes care of that works best depending on the n procs and depending on the system we are using and things like that. So basically MPI, instead of pushing this onto the user's responsibility, it pushes onto the developer of to the developers of MPI, okay, rather than from the application programmer. So as a result, we don't have to write this kind of tree-like structure global sums. So MPI directly provides us, which will, some functions which will directly work on, MPI implementation, which will work on systems depending on the optimization and depending on the, availability and size of the system and things like that. So that is basically is known as collective communication in the MPI parlance. Okay, so MPI directly provides these implementations, and this implementation is what we're going to see now. So the collective communication kind of involves more than two processes, or we can even say that involves all the processes. In our particular examples, involves all the processes in MPI communicate world. Okay, and these collective communication, because they involve more than two processes or all the processes, that is why the name collective communication. This is to kind of distinguish from the MPI send and MPI receive function calls, which basically happen only between two processes, right? And these kind of functions, such as MPI send and receive, that happen between two processes, are in MPI parlance are known as point-to-point communication, okay, which is in contrast to the collective communication that MPI provides, which works best on a depending on the system. Okay, now so it would, so what is an example of a collective communication in the context of global sum? That is basically your MPI reduce. So it says int MPI reduce is the function. Okay, now in our particular example, we said we would like to calculate the global sum. Rather, this MPI reduce not only works for sum, it also works for many other things. For example, you may want to calculate the maximum out of all the values or minimum out of all the values, or you would like to calculate something else, right? It could be the sum or anything else, right? So for all these operations, MPI provides only one function call, right? That is MPI reduce. That is one collective communication function, and that is takes in these arguments. So basically, you would have void star input data pointer, okay, and then you have void star output data pointer, okay, and then you have int count, how many values are being provided in input data and output data, and then MPI data type, right? So this is basically the data type. So what kind of data type is being used? Is it integer or MPI int or MPI double or something? And then this argument, which is the 1, 2, 3, 4, fifth argument, MPI operator, right? This basically is the operator. Now this can be either sum, max, or min, or logical AND or logical OR, and so on. Okay, you can kind of look at the list of operators available in the MPI specification, and then finally you have the regular ones, that is basically the destination process ID, right? So where should this reduced value should be stored? That is basically on process 0 in our context. And then of course you have MPI communicator, which is the communicator. Okay, so that's how you would have. Okay, all right, so that means we can kind of send our local sum here as input data, means ampersand, and then this can be our ampersand final result, right? And then count can be 1, we are basically sending one value, and then data type is MPI double, right? And then the operator is, we would like to calculate what is the MPI sum, and then destination process ID is, we would like to calculate the sum finally on 0, and then the communicator is MPI com world. Okay, so if I put in all these values, then we can call this MPI reduce function as MPI reduce, and then what we have is, you have basically the local sum, okay, ampersand final result or global sum or total sum, whatever, and then we have one MPI double, that is the data type, and then we are doing a reduction operator on MPI sum, so it's going to add the values that it receives and then store the value, final value on 0, and then you would have MPI communicate world, that is basically the communicator. Okay, all right, so you have, I mean, you know, so what we can do is now with this, so this kind of function call is going to select the best binary tree like you know, communication depending on the size of the number of processes involved and things like that, and it's going to do the best instead of leaving the burden on the MPI programmer. Okay, all right, so then now how will you use this MPI reduce in our program? All you have to do is, you can write this MPI reduce if you go back to the program, all you have to do is these lines, that is basically if my ID to all the way to here, right? So all these lines can be replaced, right, using just this particular function call. Right now we don't have to send and receive them manually. You could just write MPI reduce as we have written here instead of all these lines that I have selected, and that should work. Okay, so that can be your next version of the program, that can be V3 of the program. Okay, all right, so that is kind of what I wanted to discuss in today's lecture. So we will touch base with more on collective communication and things like that in the next lecture. Okay, I'm going to stop here. talk to you in the next lecture. Okay, thank you.